Luckily, I recorded second. So 2.6b solutions already factored and simplified, so we're good there. And when I think about the domain of a rational function, the only thing I have to worry about is making the denominator 0, and I just don't want to do that. Right? So we just list the excluded values, and if it's x plus 5 on the denominator, I just don't want a negative 5. Okay? Here's where the mistake is. That should be a negative right there in the x equals negative 5, right? Because what's going to happen with those excluded values is one of two things. It's either going to be an asymptote or it's going to be a hole at each of those numbers that would create 0. But the only way a hole can exist is if you have factored and found something to actually simplify and divide away. Okay? And because there was no simplifying to do, we have no holes. Okay? Which means that that number is a vertical asymptote instead. And it should be x equals negative 5. I missed the negative. Okay? Does that make sense? Are we good with that up to there? Okay, cool. Because the only thing left then from last time, really, that we looked at was end behavior. Okay? And so when I think about the end behavior, it's either a horizontal asymptote, right? Ends. I just want to have some arrows to shoot for, or a slanted one. And it's a conversation you are going to have in your head with yourself. Please don't do it out loud. That'd be weird. That would be like me. That's what I do, like when I'm writing these solutions. Oh, I wonder what this is. Comparing the degrees top and bottom. What's the degree of the top if it's just a constant? 0. What's the degree of the bottom if it's linear? If the degree on top is smaller than the degree on bottom. When you plug in really, really, really big numbers for x, so that's all end behavior is. You think about plugging really big numbers there, your denominator is going to get really big, and your numerator is not going to change. It cannot keep up, right? And so what's going to happen every time when your denominator's degree is larger, right? The degree on top is smaller than the degree on bottom, you will always head towards 0. Y equals 0, the x-axis will always be your target for the ends of your graph. However it gets there, from the bottom or from the top, right? From the bottom or from the top, we will always head towards y equals 0. Okay, 2 and 3 next to each other because I had the space, so I tried to save a little space. Well, let's talk 2 first. Okay, the denominator was fine, it's just linear, but the numerator was fine, it's just linear, but the denominator could be factored, so I pulled out that GCF of x with an x minus 6 left behind, but nothing to divide away, which means there are no holes. As soon as I get to here, right, as soon as I get to this realization that I'm just going to be able to factor, I can go all the way to here and say no. Guaranteed. There will never be a hole if I'm not dividing away a factor from both the top and bottom, okay? And when I list my domain, yeah, 0 from this little x over here and 6 from this x minus 6 are the two numbers I can't use. And because they don't produce any holes, they are both going to be asymptotes. They're both going to be vertical asymptotes. And you see how I wrote those two equations separately, right? X equals 0 and x equals 6. Write them as two separate equations because they're two different lines. So I want to have both of those, okay? The degree on top is 1. The degree on bottom is 2. The degree on top is smaller than the degree on bottom. I don't care about how big. As long as it's smaller, guaranteed to be y equals 0. So you plug in really, really big numbers for x, both positive and negative. The denominator is going to get humongous. The numerator is not going to be able to keep up. So you're looking at like 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion, basically 0. Good? 1, 2? Sweet. Okay, number 3. Factorable for sure, both top and bottom. First kind of factoring to always look for is that GCF. That's what I did on top. And with my first round of factoring, that's all I did to really kind of take my time. So if you're reading this kind of one by one, you could kind of hear my thoughts. But then I keep going, right? The top had x squared minus 4, so x plus 2, x minus 2. The denominator was just a quadratic, so I just, two numbers that add to 3 and multiply to negative 10, so x plus 5 and x minus 2. And look at that, an x minus 2 up top and an x minus 2 on bottom. So these two are gone, right? X minus 2 is gone, x minus 2 is gone. And there's a simpler version of that function. It still needs to be said, though, that both x minus 5 from this factor and x equals 2 from this factor both don't work. I know I divided those away, but the original function still had that x minus 2 in there. So those are my two excluded values. But because the only one that's left when I'm done is the x plus 5, that's going to be the vertical asymptote, right? The hole exists at the x value from the factor that I was able to divide away. There it is, 2 comma something, right? It's a point, right? Asymptotes are just lines, so I just need the equation of a line, but a hole is an actual, like, there's a physical hole in this function. I need to know where that's going to happen. So I got to find the x value that goes with it. How do I do that? Well, I take the simplified version. I kind of rewrote it down here, and I plug in 2 wherever there's an x. So there's an x, now it's a 2. There's an x, now it's a 2, and I see what I get. Well, 8/7. It's kind of hard to make really, really nice results there for those holes. So when we plot that, we'll go to 2, and then up to 1, and then just like a little bit, right? Because that's 2.166666666, right? Every 1/7 is 16666 repeating. So we'll just go a little bit above 1. I'll put a hole. All right, we'll get to that tomorrow. That'll be it tomorrow, kind of thing. Okay. But when I think about M behavior, again, comparing degrees, now I've got 2 on top. It's quadratic, and 2 on bottom. Right? Degrees are the same, which means when I plug in really big numbers, squaring them, they're still going to be the same. And so you don't have a horizontal asymptote at y equals 0. You have a horizontal asymptote somewhere else. And that location is the ratio of your leading coefficients. 2x squared over 1, x squared, 2 over 1, y equals 2. Okay, so it's a lot to keep track of and remember, which is why you're going to need to prepare for 1 week from today. Okay. All right, number 4, which I think is the hardest one in terms of the factoring aspect of it. This is where a calculator is going to really come in handy in case you don't have it. And you're going to need it for today anyway, so we'll probably start taking those out as you get ready. But up top was the difference of cubes. And it doesn't happen super often, but I want to try to keep this stuff fresh because it is some of the new stuff that we've done. So x cubed and 2 cubed. And a lot of us are still writing x minus 2 cubed, or x minus 2 and x plus 2 and x minus 2, and just kind of making it up. That's not going to work, especially as we try to find a large collection of other points that we're going to want to plot along the way. 2.7, we're actually going to graph these things. You got to be able to factor these correctly, right? X and 2 are my numbers. I don't think of x cubed and 8. I think of x and 2, right? X cubed and 2 cubed. X, 2, x squared, 2x, 2 squared. Every time. X, 2, x squared, 2x, 2 squared. Same sign, opposite sign, always positive. And the nice part about the difference of cubes is that this leftover quadratic, whatever that second factor is, will, 1, never be factorable. Ever, if you did it right. And 2, it'll never give you real answers anyway. So it's not even going to be irrational. Those are always going to be imaginary. So you're not going to have to worry about finding zeros up top for that factor, which is nice, okay? But the denominator, I did this on purpose. Okay, I made a denominator that wasn't kind of clearly algebraically factorable in any of the ways that we've got, right? It wasn't quadratic, it's cubic, so, you know, can't do it that way. And it wasn't sum or difference of cubes, and it's not factoring by grouping, because look at the coefficients, you don't have common ratios that work out real well there. So if I want to factor that denominator, I have to hope and pray and cross my fingers that I've got some rational roots to get me started. So what I did is I went to the calculator and I typed it in. I went to this calculator. That's not a calculator. I restarted. I went to my calculator. I just went to y equals and I just typed in the function from the denominator only. Like I just typed in the denominator. I didn't even type in the whole function. I just went to y equals and I typed in the x cubed, whatever. It's going to take too long for me, huh? I typed in the denominator. And I said, all right, if I want to find some rational roots, because those are really nice, how do I do that? Well, all the factors of my constant over all of the factors of my leading coefficient, right? All the factors of 6 over all the factors of 1. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And I typed all those in. So 1 and -1 and 2 and -2 and 3 and -3 and 6 and -6. And it took me all of like 5 seconds to type those numbers in. But what I saw is I got like something, 0, 0, something, 0, something, something, something. And that this and this and this all gave me 0. Which means if x equals -1 is a 0, then x plus 1 is a factor. Same thing for 2 and for 3, right? And if it was cubic to start and I found 3 zeros, ta-da, I'm done. I'm done looking. And I can just, boom, write the factors. And factoring just got so much easier if I use a calculator to help, okay? So that's why I put a trickier one on there to try to push us a little bit to go looking for those factors. And then we get there, oh look, an x minus 2 on top, x minus 2 on bottom, boom, boom, those are gone, and there's my simplified version. And I still have 3 zeros that I have to worry about to make the denominator 0. So there's my list, right? But only 2 of them are asymptotes because there's only 2 left. This x equals 2, 0, right? That x minus 2 factor is going to produce a whole. And so I came over here and I said, all right, let me take the simplified version of that function. I'll drop in 2, whatever I get. And I cannot believe how nicely it worked out to actually give me just -4. Perfect, boom, -4, 2, -4. Same degree, top and bottom, so ratio of your leading coefficients, 1/1 for my horizontal asymptote, y equals 1. All right, last one, and then we'll get to 2.7. Okay. I put this one in here because I wanted to at least see what happens when our degree on top is larger than degree on bottom. But I'm going to go through the whole process of factoring and simplifying if I can. Factorable, yes. Simplifiable, no. So since we didn't divide anything away, there's no holes. No division, no holes, okay? -1 is the only problem spot for me along the way, so that's going to be a vertical asymptote. But if I want to find the end behavior and the degree on top is larger than the degree on bottom, you do not have a horizontal asymptote, you have a slant asymptote instead. And to find it, we actually divide. Whether you use polynomial long division, or since the denominator is linear, we could use synthetic division as well. So choose one option or the other. Just don't forget the 0x that's missing, right? So x squared plus 0x minus 9, or 1, 0, -9 as your numbers there. Divide. It's just going to be y equals whatever your quotient is without the remainder. This x minus 1 right here, or there are my coefficients for my linear term, x minus 1. Okay, and we're actually going to, when we do that, when we actually graph that, we're going to graph that line. We're going to go to -1 on the y-axis, plot a point, and then follow the slope. Slope is 1, so up 1 over 1, up 1 over 1, up 1 over, and we'll dot that line as a good kind of guide for where we want this graph to go. Because that's what end behavior is. It's a target for us at the edge of the graph. Cool? All right, rock and roll. Let's do this thing. 2.7 just has us start looking at sketching these. Let's actually get to the point where we can graph these by hand. So what you're going to need is some graph paper. If you don't have any, raise your hand and I will give you like 3 or 4 sheets right now so that you can use them over the next couple days. You're welcome. Okay, when it comes to the in-class or the take-home test that we'll do, you're good. What we'll need is just a straight edge. I will provide empty spaces for you, which means we're going to need straight edges today too. Does anybody need a ruler? Because I'm going to use that as a straight edge. Now, there's lots of straight edges around the world that you can use, like the edge of a, you know, the edge of your driver's license or a credit card, because we're not going to make these graphs all that big. Got one. Okay. Nice, that's awesome. Okay, so let's do number 1. And we might only get, honestly, that far, because I'm going to really take my time so you see the process, which means tomorrow we're going to try to do the other 4. Now, I might like drop one of those, but I really like all 4 of these examples. So I wanted to try to do all 4 if we could. But we're just going to do number 1 to start right now. And in a couple seconds, people at home, I'm going to stop sharing my screen so you can see the bigger version of me working through this. And then I will point you back at it when I actually do my graph. Okay, and that's going to happen right now. Where are we? There we are. Stop presenting. Okay, cool. So it is really mostly about what's on the whiteboard right now. Okay, so there's our function. 3 over x minus 2. And I picked a super simple one to get us started. But no matter how complicated these get, the process doesn't change. Okay, and you're going to see that the process really starts the same way everything did in 2.6. What's the domain, right? What are our excluded values? On all that stuff that we've been talking about, let's first factor and simplify. Yay, done. Moving on. Nothing to factor, nothing to divide away. In this one, there might be in other ones, so we always want to start there. Let's first start thinking about the x values that don't work. What's the x value that's going to give us a problem? Cool. Now, the question we want to ask ourselves from here is, does that create an asymptote or does that create a hole? Asymptote. Why? Because it's only on the bottom. Only a 0 from the denominator. It would have had to have been something we divided away to be a hole. So I know that because we didn't do any division, I know I don't have a hole. Instead, I have an asymptote at that spot, and I write the equation of that line, which is x equals 2. Okay, and we're going to dash or dot that line when the time comes to actually do that. Okay, and then the only thing left in 2.6 is to figure out what's happening when x gets really big. Right, what's happening at the ends of this graph. And it's only going to be either a horizontal asymptote or a vertical one. We just have to figure out which one. And that's a conversation you have with yourself, again, about degrees. Degree on top, what do we got? 0 degree on bottom? Degree on top is smaller than degree on bottom, so we are guaranteed to have a horizontal asymptote at y equals. You guys are awesome. God, I love this class so much. There you go, 2.6 part, done, okay? That's all of our knowledge that we have so far. It's time to start filling in points that actually exist. That's all the stuff that doesn't exist. I want to think about parts of this graph now that do. And don't draw this, but I just want to give you a visual to look at. If I'm going to be graphing on a set of axes, what do you think would be the kind of points we definitely want to plot and plot correctly? If this is the plane that we're working in, these are our guides. Intercepts, absolutely. If there are any x-intercepts or any y-intercepts, I definitely want to make sure those exist. And I want to figure them out to start. X-intercepts, if there are any, and a singular y-intercept, if any at all, right? We can have as many x-intercepts as exist, but we can only at most have one y-intercept, otherwise it wouldn't be a function, right? So I'm actually going to write down what, like for this graph over here, but because this is new, I also wanted to kind of come over here and write down in general how to find these kind of intercepts, okay? And then we'll apply it to this function itself. All right, x-intercepts happen when y is 0, right? Because you're not going above or below. And these numbers are just going to be real numbers, right? They're going to be some constant, right? So I'm just going to call it C. But the question is, how do we find those constants? Well, when you think about like what we're dealing with here with these rational functions, I've got a fraction, and I want to figure out what x value to put into this fraction that's going to give me 0 as an answer. I'm not plugging in 0. I'm setting a fraction equal to 0. And I want to figure out what's going to make that happen. So don't think about that one, but just fractions in general. How do you make a fraction equal to 0? But if I put a 0 on the bottom, are we allowed to divide by 0? Remember, that's going to be an asymptote or a hole at that spot. So this number cannot be 0, right? You have this denominator that's non-zero. Because if it was, it'd be undefined, and I'm not getting an answer at that spot. It's either an asymptote or a hole. And I appreciate that, because it brought up a really important part, that that denominator really just can't be 0. You've got to be 0 on top. Okay, so I don't care about the denominator being 0. In fact, I really want to make sure it's not. But realistically, we've kind of taken care of that like way over there by factoring and simplifying if that was an issue. And so all I really need are the zeros from the numerator, that's an n, only. Okay, figuring out what x value I could plug into the top to make it 0. And maybe there's 1 or 2 or 3 or 4 or none, right? We could run into that case where we don't have any at all. So let's do it. Let's look at the numerator. Can you plug in an x into that numerator to make it 0? There's no spot for x, right? So in this case, there aren't any. And that's okay. We don't have to have x-intercepts. It's all about the degree of that spot. If the degree is 0, that's how many x-intercepts we have. If the degree is 1, that's how many we've got, right? If the degree is 2, well, it could be real or it could be complex, so we got to be careful. Sweet. All right, x-intercept's done. How about the y-intercept? At most one of them, right? And it's going to be at some point where x is 0. Now this is us actually getting to plug in 0 and figure out the y value, some constant, so I'm going to call it c again, that we get back. And so think about what happens when we actually go through and we plug in 0 for all of the x's. And it doesn't matter which ones we're looking at, right? You've got this x over here, okay, now it's all 0. Or you've got like this and this, and they're all 0. Or all of this is all 0. All of this all just disappears. What's left if every x value has become a 0? What's the only part of any rational function if all of the x's are gone? Just a constant, okay? That number will be the ratio of your constants. Okay, so not a whole lot of work to do there. Just ignore all the x's because they're really just becoming 0. Okay, now we've got a constant on top and a constant on bottom, so we're going to get ourselves an answer. Okay, look at something like number 2 though, real quick. What's the constant in the denominator? Can we divide by 0? So we wouldn't have a y-intercept in that case. Okay, so just be careful. Okay, but we're good here. We got a 3 on top and a -2 on bottom, so -3/2. Or -1.5, since that decimal has an n to it, we can use it. Sweet, there they are. There's all the intercepts. Let's start graphing. Let's see what happens. Okay, I'm gonna move this. It's gonna be a little glary, sorry. There's not really much I can do about it. Because the glare is coming from the actual projector, not the lights. All right, so break out your graph paper, break out your calculators if you've got them nearby. I'm going to break out my graph paper. There it is. And because we have to sketch this, we're just going to do the best we can. But a lot of what I want you to kind of start to be comfortable with is the fact that no matter what, when we draw straight lines, we need a straight edge to do it. Okay, so we cannot freehand straight lines, but we are going to freehand everything else. Okay, so it doesn't have to be relatively big. It can be just like a quarter, maybe half the page. Let's give ourselves a set of axes. I don't know. Here's a good spot. Ignore some of the stray marks that happen towards the top. It's imperfect as I get closer to the top. So this right there doesn't really exist. Okay. Sweet. Don't make it too small. Too big is okay. Too small is no good. And what do we need to kind of fill out graphs? What do I need to add to this set of axes in this plane to make it complete before I even plot any points? I need a scale. I need to know how big every box is. Okay. Now, we don't really know how big we want to make it yet. So a good, just first guess, is just 1. Right? Make every box worth 1. To blow it up, I'm going to make every like solid lines box worth 1. Okay. 2, 3, 4, 5, 6, 7. -1, -2, -3, -4, -5, however far you can go is cool. And we'll do the same thing up and down. I like every box up and down to be worth 1 as well. I can only go that far. That's what I've got. If you want to write down 1, 2, 3, if you want to write down every single number, fine. That's up to you. It gets a little cluttered. For me, the bare minimum, tell me what 1 box is worth left and right and what 1 box is worth up and down. What else? What else do we need before we can plot points? What's that? Label axes. I got to know what everything is, what we're talking about. Like, what are we comparing? Well, we're comparing x to the function g of x, okay? If you're only graphing 1 function at a time in a set of axes on a set of axes, which we will, we're never going to graph more than 1 at the same time, just label your y-axis with that name. Again, ignore the weird stray marks that happen and stuff. Only one more thing, one more set of things. Arrows. These graphs go on forever. You got to tell me that. Good. All right. Now we can actually start graphing. And I'm just going to go through what we've got, and I'm just going to put it down. Okay. So domain can't be x equals 2. So what's happening there? Oh, I have a vertical asymptote at x equals 2. That is a vertical line, and I'm going to dash that line. So I'm going to go to 2, and I don't have a straight edge, but you do. You have to take the straight edge, line it up on that grid line, and I don't care if you draw the whole line and then erase sections to make it dashed, or if you just dash it. I usually cut through the axis with one of my dashes. Put arrows on the ends so we know they go on forever. Because those arrows are going to be our targets. Remember, as a graph approaches an asymptote, it approaches the arrows. Okay, whether it's horizontal or vertical, those arrows are kind of the thing we want to get really, really close to as we go. Sweet, done. Vertical asymptote drawn. No hole that I have to worry about. Cool. End behavior, horizontal asymptote. Okay, I got to draw that one too. But that's the x-axis. It's already drawn. And so how are we going to make that obvious? Well, for me, color helps. But if you're just sitting there with pencils, how are we going to do that? Well, one option is to draw your asymptote thicker than the axis that you're covering. One option. Another option, go like right above it, like just above that line. Another option, go like right below it. That's cool too, whatever you want. Or you just color right on top. Now, here's something I suggest you do no matter what. If you are graphing an asymptote on an axis, draw your asymptote beyond your arrows of the axis. You can see my red asymptote sticks out beyond the perceived edge of this graph. Okay, and even better, just put like HA on one side. Horizontal asymptote, so super obvious what that is. Okay, but it's got to be dashed because it's not really part of the graph. You're going to see when we type this thing into y equals and we graph these, which of course we can, which is why for me, what's up here is going to be way more important than the graph because you can just graph it. You have a graphing calculator, I know that. If this was any other year, we would do this without a calculator. So you're welcome. Cool, there it is. There's my horizontal asymptote. Okay, no x-intercepts to plot. Awesome. Okay, what about a y-intercept? I'm going to change colors because here's where the graph actually starts. Y-intercept at 0, -1.5. Okay, so -1, -2, right in between. Sweet. That's it. Do you think that's enough to graph this thing? We need so much more to get a sense for what this graph is going to look like. All right. And so what do you think now that we have intercepts and we have all of those asymptotes, those guides, those targets for ourselves, what else do you think we need to be able to really sketch this graph? A whole bunch more points. Okay. This is where the calculator does the rest of the work for you. Okay. But you want to have an idea of where to look for those points. Okay. And so what I want you to start noticing is that asymptotes and intercepts, the things that we've got so far, are breaking your graph into sections. This section to the left of the first x value where anything existed, in between the first x value and the second x value where something happened, between the third and the fourth and the fifth, however many things you've got, it kind of breaks it into sections. And right now, if you look at, I'm going to bring you back with me, because the rest of my work right now is going to happen up here until I actually get myself a whole bunch of points. So I want you to notice that the number of X values that we've written down right now is 2. That means I've got 3 sections to fill in. To the left of the first one, in between the first and the second, and to the right. Okay? If I had 3, like if I had a vertical asymptote, an x-intercept, and a y-intercept, and they were all unique, 3 x values, I've got 4 sections to fill in. 1 to the left, in between, and 1 to the right. 4 things, I've got 5 sections. 5 things, I've got 6 sections, right? Now, what I'm going to do on the board here is not the way you have to do it. But I'll tell you what I'm about to do right here is what we're going to do in calculus, how I'm going to design a space to fill in those sections. And so if you start getting into the habit of doing it my way, it's really not my way, it's the way to do it. It's going to help you stay organized. Okay, so what we're going to get is a collection of points. Okay, and the more points you've got, the easier this thing is to sketch. Okay, so I've got 3 sections. I need at least 3 more points. I'm going to find way more than that because it's all going to happen in the calculator anyway. Okay, and so here's what's going to happen. I've got this first section that kind of starts like it goes, from negative infinity all the way to something, and then I'm going to stop at that first x value, and then I've got this section, and then I'm going to stop, and then I've got this section, right? And so I'm going to go from negative infinity all the way to infinity, and I'm going to write down some points. So interval, stop, interval, stop, interval. And I know what's happening from left to right at each of these spots. And if I look at the x values that I've circled, I've got x equals 2, and I've got x equals 0, right, at the y-intercept. This is not right. That's not 0, because I want to go from left to right. The first x value I'm running into is 0. The second one is 2. And I know what's happening at x equals 0. It's the point, negative 3, 0, negative 3 halves. And I know what's happening at x equals 2. That's a vertical asymptote. What I want to try to do is look in these sections, starting at the beginning and ending at the end, and just plot a whole bunch of points. Okay, so I'm going to look from negative infinity all the way to 0, my first x value, and I'm going to get myself a bunch of points. Why am I going to get a lot? Because this section is huge. I don't know, like at least 3. The more, the merrier, guaranteed. You want to find 1, nah, probably not enough. 2, better. 3, even better. 4, 5, 6, just write them down. Okay? So from negative infinity, the beginning of the graph, to that first x value where I need to stop. Okay? Then from this x value to this one, I just want to look in between. This is an interval from 0 to 2. Okay, so up here are intervals and stopping points, if you want to call it that. Okay, this right here are just sections of the graph broken up by intercepts and asymptotes. Okay, within those sections, I want to find a whole bunch of points. Now, this section is not very big. 1 point will do it. The bigger the section, the more points you want. Okay? So from negative infinity to 0, stop at 0. From 0 to 2, stop at 2. From 2 to infinity, and then we'll be at the end. Is this section large or small? Let's find a bunch more. And I'm going to let the calculator do all the rest of the work. I just need to know what x values I want to plug in. And so when I think about like the beginning of this graph, negative infinity to 0, I mean, we kind of designed our space already, right? Which I think, and I did this on purpose, I think is jumping the gun. I think designing your space before you have a collection of points might be hurting you in the long run because you don't know what any of these points are going to be. And if I design a space, it only goes from -4 to 5 on the y-axis, but what if these numbers are bigger or smaller than that, right? We want to be careful. So I did that on purpose to kind of teach you that part of this. Don't graph until you do all of this. Then design a space that works. But when I think about plugging in numbers, any number between negative infinity and 0, I'm definitely not going to pick like -5 million. I want to pick numbers pretty close to this one. And I want to pick nice ones. So pick a number between negative infinity and 0 that's pretty close to 0. That's really close to 0, but make it nice. -1 sounds great. Give me another one. -4, awesome. What about another one? -2, great. We're missing one. Why not? Let's throw it in there. Love it. Let's try all 4 of those and we'll see what we get. And we'll do them all at once. Let's fill out this whole table and then we'll jump to the calculator. Okay? -5, -6, whatever you find that you like. And if you don't like the y that goes with it because you get some weird fraction, some long decimal, lose it. Pick a different one. Right? You have total freedom as to what numbers you pick. Okay? Now we're between 0 and 2. A number bigger than 0 and less than 2. Pick a nice one. Going halfway is always a good idea. Okay, so if you're going from 0 to 4, pick 2. And maybe pick 1 and 3 also. But that's okay. Definitely going to pick 1. Now here I want to be bigger than 2, less than forever, but I want to be close to this. This makes it so much easier to graph. Pick a number bigger than 2, and love it. Let's see what that does for us. Okay, let's try those. I'm going to jump into my graphing calculator. I'm going to plug in y equals. You know what I'll do is I'll actually just share for a hot second this screen. Hopefully this will let me. Yeah. All right. So in y equals, I'm just going to type the function. Okay. Now, because my denominator is not a monomial, you need parentheses around it. Top was just a monomial, right? Just a constant. So I'm good. 3 divided by parentheses x minus 2. And if I go to the table, and if it's already set up so that your independent is set to ask, we can plug in whatever numbers we want. We don't have to go searching for them. And if we like the results, we'll use them. If we don't, we'll drop them and we'll pick a different one. Let's see what happens to -1. Love it. -1. What about -4? That's not bad. We're going to get some decimals. It's okay. It's not a bad one. No, that's not a bad one either. How about -3? That's okay. 0.6. It's not the worst thing in the world. It wasn't like 0.42937, whatever. It wasn't irrational or just an ugly version of a number. That might be a little more than we need, but that looks great. That's fine. Okay. Let's see what happens at 1. Oh, love it. -3. Beautiful. How about 3, 4, and 5? Oh, those are great. Love it. Write them down. Write down those numbers. Okay. Again, remember, I know that you have a calculator sitting in front of you that you can just type in the function and press graph and try to match that graph. Okay. I'm not going to be looking nearly as closely at the graph. I'm going to be looking at this. This, to me, is what matters. Okay, what I want to be able to try to do is see the picture of your graph without you actually graphing. How do I see that picture? I look at the work that you did, like this, right here, that I went with. Okay. Oh, where'd it go? Come back. There it is. So -3 was -0.6. That's okay. That's not too bad. 1 was -3. 3, 1.5. And 1. That's a nice little collection of points. Now let's plot them and see what happens. And again, this is going to be the only one that we get to get done today, which is fine because I'm going super slow so that you get it. All right, whiteboard. All right, let's plot these points. Let's center you back up again behind you. angles. Ta-da. All right, plot some points. We didn't necessarily write them in a great order. Maybe we'll do that better next time, but I'm just going to plot them where they really go. Okay, -1, -1. -4, 1, 2, 3, 4, points -0.5, so halfway between 0 and -1. -2, halfway between 0.5 and -0.5 and -1. And then 0.6, just a little bit below. Like, do your best. All right, something like that. All right, so there are all the 4 points that we found in that first section. And we're starting to get kind of a feel for how this thing is going to be connected. And remember, these are just ratios of polynomials, so they're going to be smooth, rounded, connected from one side of the section to the other. And we'll see what that connection looks like. All right, well, 1, -3, so that's down there. 3, 4, was it 1.5? 4, 1.5, and then 5, 1. Again, excuse the stray marks that show up where they shouldn't, like that one, and that one. Okay, cool. Now, how do we connect these points? Okay. Well, remember, your asymptotes are your targets. Okay. Let's talk a horizontal asymptote first. There's my target. The left edge, there's an arrow right there, which means that that's the direction I need to be heading towards as I move towards that arrow. And you can kind of get the sense just by like following the points that you've got so far of what's going to happen as we get closer and closer. And you would see, if you plotted more points, that it would start to look like that. The more points you have, the easier this thing is to sketch. And so what I want you to start realizing is that if you do have, because we don't have those, if you do have a target, you just have to know, am I going to go right below it or right above it? Because I'm never actually going to reach that arrow, but I'm going to be close. And since you can see the trend of this graph all exists below this asymptote, then the arrow on the end of this function, right, negative infinity is how far we're going to go, is going to exist below it as well. And so what I do is I give myself an arrow either right below or right above, depending on where those points are in that section. And same thing on the right side, right? I've got these points here, all existing above the horizontal asymptote to the right of that vertical one. And I'm telling you, if you plot more points, this gets a whole bunch easier. You would see the trend of this graph to look something like that. Okay, now we don't have any of those, so let's back up a little bit. We only have those 3 points, but I'm telling you, the more points you have, the easier this thing is to sketch. But you know that your asymptote is your target. And if I have an asymptote right here, I'm going to have an arrow either right above it or right below it. And since my points lie above the asymptote, then so will my arrow. Okay, so when you draw in your end behavior, your arrows are going to be right next to each other. Your asymptote arrows and your actual graph arrows. Okay, but what about the vertical one? Well, follow the trend of the points that you've got. Okay, and if you can kind of visualize connecting these points moving towards the asymptote, do you like get that sense that you're going down? Remember, as you approach a vertical asymptote, you're either going up as you get there or down as you get there. Okay, these arrows are your targets. Okay, and if I'm heading down on the left-hand side, then on the left-hand side, pointing down is where that arrow is going to be. Okay, same thing on the right over here. As I move towards the asymptote, from right to left, up I go. There's going to be an arrow up there. Worst case scenario, press graph. Just look at it, right? Now the idea is to connect one arrow to the other, not crossing your vertical asymptote. And the graph with one vertical asymptote is about as simple as it gets. And I know that that took forever to do that. when we start doing these, now that you've got a hang of what this thing looks like, it should be a whole bunch easier. And what I always try to do then is actually like, hey, that's my graph. Let's compare it on the calculator. Ta-da. Perfect. Okay. It's even blue too. I remember that was pretty good. So there you go. So this process, 2.6 though, find some intercepts and then get a collection of points to help you graph. And the more points you have, the easier this stuff gets. There you go. Chapter 2 done. Now it's just time to practice. Okay. So 2.7, we're going to try to practice a bunch of them tomorrow virtually. So join either second or fourth. I will have probably by tonight a list of what to expect next Wednesday, Thursday. And then on Tuesday, when you get here, and I might even send it out before that if I get it done before that, I'll have the review from all the complex number stuff from 2.4, 2.5 with the fundamental theorem, and then all the rational function stuff to go. Adios. Thanks, everybody. Welcome back. I will see you live at some point tomorrow, please. Thanks, guys. Thank you. Thank you. Any questions, folks at home?
Oh, no, you're good.
Sweet. All right. I will see you guys. Bye. Have a good day.